our next speaker is Peter Neuhaus, and Peter and company have a new paper that just came out in Animal Behavior that I found very interesting indeed, and he's going to talk about that today. And if he's sharing his screen, we've got it. So Peter is affiliated with University of Calgary. He's been working in the working with Catherine Ruxtel on the sheep river population of bighorns, and he'll be talking about some of this work this afternoon.
Okay, thank you very much. So there were some really interesting talks so far. I will circle back to the topic that Marco and Niels were talking about selective hunting and the size of the sheep. The sheep you see here in my title page is actually kind of a record sheep. It's the oldest ram we ever had at Sheep River in a population that has been followed since 1981. So he's 15 years right now, so happy birthday, 614. Now I have to move. The same problems as Marco had before. Oh, there we go. This guy was a real record ram in terms of the hunting society, the Boone and Crockett. He was the #1 for several years, also from the Sheep River population. I don't have to go into details because Marco did that for me before. So he told you about these two papers. The influential, very important paper in Nature from 2003, and the rebuttal kind of in PNAS from Trail, Schindler, and Coulson. That was kind of saying, well, yeah, there might be something, but it's impossible to show in this short period of time. So there is definitely problems with both these approaches, as well as the animal model approach from Dave and colleagues, as well as with the PNAS, where they used integrated projection model, an IPM. So the main problem is all these studies are basically, let's say, talking about genetics while they are actually measuring a phenotypic trait, which is very plastic. We know if they have more food, if they have a harsh winter or a less harsh winter, it has a big impact on the size of these traits. And Marco said in his talk earlier, 30% is genetics, the other 70% are environmental factors. And the big question is, the 40 years of data that were used for this 2003 paper are very, very short for a relatively long-lived animal as the bighorn sheep to actually show a genetic impact. But if it is not genetics, what else could it be? I mean, the Coulson paper, they didn't show much. I mean, they said some environmental factors, maybe stochasticity or whatever. I think a lot of the papers we've seen on these 2 days, and they are good papers, they are missing something. It's behavior. The animals are not just measurements, they are not just GPS locations, they actually do things and they have to make decisions what they do and when they do it. So I introduce here in this discussion a trade-off between the time during the rut, the time spent in low energy and energy gaining behaviors such as feeding, ruminating, or resting, versus the time spent in the rut. So searching for females, going from group to group, tending a female, or being involved in coursing changes. Because there's only that much time, they can't do both at the same level. And the idea is that if they spend a lot of time in this, in the rutting behaviors, they just don't have the same energy to grow horn in the next year or body size. So to show this in a picture here, there is this 2.5-year-old ram. He has a red block of energy or time during the rut, and he has to decide what to do. He has a very slim chance of reproducing, but if there is a coursing chase, he might take part or he might not. But he should spend most of his time investing into future reproduction. So spend a lot of time and energy into resting and feeding to have a lot of horn growth in the following year. If you are like this guy, 7.5 years old, you would probably in a hunted population not live anymore, but in this non-hunted population, he is not at the top yet. He's probably about the fourth highest ranked ram right now. But he has a good chance of siring offspring. So he spends a lot of energy, a lot of time in rutting behavior, much less time, and and lacks energy gain through in feeding and resting. So to show this, I needed to build a model. So I needed a modeler. So I found Susanne Schindler, who has been in some of the papers on these topics before. I met her when I visited her and Tim Coulson in Oxford a few years ago when she was postdocing there. And we started working on this paper. And we have the long-term data set. Here you see Catherine with a ram that we measured about 3 weeks ago when it was brought into the office in Cochrane. So this is the paper underneath that just came out that Mark was talking about. Here, this is just to show you what kind of empirical data we used. On the left is the survival data. This is from 250 female sheep and 268 rams going back to 1981. And we have horn increments only from animals that we were able to measure. So there's some that were poached or died a natural death, or they were legally shot outside of the park, like the one you saw in the picture we were measuring the other day. So the model, just very, very crude. It's a relatively complex model. We needed a mathematician for it. Susan is a mathematician by trade. So we started with 100 males and females at the age of 2 and let the model run with time steps of 1 year until we had all age classes available. We put in natural mortality so that we had of following the sheep river data, natural mortality that should be close to a non-hunted population. Male horn growth every time we had a new time step starting, the males got their horn increments added. Here it ends with empirical data, but we invented kind of, or we added a trade-off. So this is an assumption that every model has assumptions, a trade-off between the rut participation and horn growth depending on mating rank. Mating rank was following by the horn length. This is obviously not exactly how it works in nature, as Neil said before, but this was our approach. The longest horn was the highest ranking male. The highest ranking male invested most in reproduction, so he had less time feeding during the rut, and he had a little bit smaller than expected horn growth in the next year. And if you're low rank male, you were able to increase a little bit more, your horn growth next year a little bit more in this model. And after these 16 years, we invented hunting. So hunting was brought in, and only rams that were legal age or legal size were allowed to be hunted. Quickly through the main results here, just what you would expect in this is proportion of legal rams that are removed. In those that are high pressure, high hunting pressure, we have a very high proportion of young males in the population and very few old rams. Here we see the female curve, if you want. Line is the female proportion of different age classes, and the male is pretty parallel in unhunted populations. They have a little bit higher mortality. That's why it goes below the line of the females around the age of 8. Obviously, 2- and 4-year-old rams were not shot. They were not legal. So we have them the same in the right graph here as in the different hunting scenarios. Interesting, 10-year-old rams in the non-hunted area, or in the area where only 10% of the legal rams were removed. There were basically no 10-year-olds in where 40% or 70% were removed. Then quickly to the average mating rank. Interesting here, 2-year-old rams in the low hunted or unhunted area, they did not take part in the rut. And the other interesting thing in this graph here on the left-hand side is the average mating rank at the age of 6. We see that a 6-year-old ram in a population where we removed 70% of the legal rams is basically a tending ram. It's a close, if not the top male of the population. While in the unhunted population, we're close to the middle of the pack. I mean, there's no way in an unhunted population a 6-year-old ram is actually a tending ram. He is a courser. I mean, probably a pretty successful courser, but he's a courser. That's interesting. And I mean, these are results from a model. These are not real data. And then here, the horn lengths, we see maybe quickly that already 2-year-old rams start to get a little bit shorter horns in highly hunted areas. I want to look at the horn lengths in this graph, where we basically have the simulations. There's 10,000 simulations done, and we have the stochasticity in and everything. And we start at 0 when we start after these 18 years. And we, in some populations here on the right, 10% harvest is brought in. So every time step, every year, 10% of the legal rams get removed. Here it's 40%, and here it's 70%. What is interesting here is that we have a decline already in the of horn size already in the 10% harvest area. It's very slim, but it's 5 to 8 centimeters with our assumptions. But after 10 years, it just levels off. It is constant afterwards. The same is happening in the 40% harvest and in the 70% harvest. Interesting, in the 70% harvest, the horn decline is close to 20 centimeters. And after 10 years, the horn length of an 8-year-old ram is approximately the same as the horn length of a 6-year-old ram at the beginning before the hunting was started. So this is just the whole population. I just want you to look at the very last line here, which I think is quite stunning. We have 20 in the population. If there is no hunting, we have 22.5% of all males are 8 years old or older. While if we go to the 40% of removal of rams, we don't only have obviously much fewer rams. We see 482 rams instead of 610 rams. There's only 7% or even a little bit less than 7% of those rams in this population are of the age 8 or older. Now, very quickly, the model shows what we expected, a strong rapid reduction in horn size due to the plasticity in energy allocation. So it's behavior, I say, between the rut and the horn growth. There is no change in allele frequencies because we just didn't put any change in allele frequencies in the model. It doesn't mean that there isn't any. And it applies specifically to selective removal of trophy animals. What we don't have, and which is not so surprising, is actually proof or empirical data that this happens, that the energy expenditure during the rut has an effect of the horn growth afterwards. You have to imagine, you have to watch the rut and measure those rams a year and a half afterwards to see how much the increment of their horn is. So this is very difficult, and that's why there is nothing in the literature until now. So this is Christian Village. He was my PhD student on ibex. These are ibex. You've seen them in Marco's talk briefly. They are a mountain goat living in the Alps. So Christian Village is just a great outdoors guy. I mean, you have to watch those guys during the rut. He's a great photographer. He did take thousands of photos, which were very important in this. And he's a great biologist as well. I mean, he really sticks to the stuff and figures out how to do things. Being in my lab, he had to study behavior. This is just a given. So he studied the behavior, how much time the animals, the billies, I guess we say, because they're goats, spend rutting, how much time they spend feeding during the rut. And he figured out a good way to use his photographies to measure the horn increments after the fact. So you can read about this in Mammalian Biology. We published this in 2013. Now quickly to those results. The behavioral results first. There is a higher proportion of young males on the top here that are taking part in feeding and ruminating activities, and older males do less of that. That's as expected. We have seen that before. We know that tending rams quite often actually don't feed pretty much at all during the mating season. Proportion of time spent in rutting behavior, which are very costly, is walking from group to group, finding females, sniffing them, tending them, coursing, running after them. It's very energy intensive. We have very little in the young rams, or yeah, I say rams, billies. They spend more time feeding, but approximately starting at the age of 7 to 12, there is a huge variety. There's some older males that don't do as much, and some do very, very much. How does that translate into the horn growth in the next year is the big question here. So these two graphs are a little bit complicated. They are transformed because there's different age classes, so they had to be transformed, and there are residuals. Residuals means the 0 line is the actual mean horn length of this of a given age class. Everything above is they gained more size than the average ram, and below is they gained less increment in the following year than the average ram. So we see there is, and it is significant, barely, but it is 0.05 positive correlation between the feeding and the ruminating and the increment of the horns. And on the other side, we have the tending coursing. The more time you spend in tending and coursing, the less horn increment you gain in the following year. So this was a very important, this is going to be a very important paper. It will come out sometime next year. We are revising it right now. It's a very important paper because it's the first to show trade-offs of energy expenditure during the rut to the horn growth in the next year. And this is something that a lot of people always thought that's not possible, because during the winter, the horns stop growing anyways. The next spring, they start growing again, and there is no rut then. So to conclude these findings, having added this IBEX stuff, the model per se shows energy trade-off between the rut and subsequent horn growth. And this can lead to a fast decline in horn size without the need of genetics. That doesn't mean there is no genetics, but that was the main reason I wanted to, or the main thing I wanted to show, that a mechanism like this could happen. The cause of the decline is selective removal of the high-ranking males, as given by the model design. And very interesting, I think, was that the decline leveled off after about 10 years and stayed stable thereafter. So there was no further decline in horn size after 10, 12 years. The model in general is pretty conservative because it does not include higher mortality for younger males, for example, if they have to, or if they take more this energy expensive rut behavior on at a younger age, as naturally would be the case. One could expect that there is higher mortality there, actually. I want to make very clear, a high proportion of big males are removed over a prolonged period of time on unreversible genetic change has to be expected or can be expected eventually, because these are costly traits. They are selected change sizes, sexually selected sizes, and you expect that that if you do that over 10, 20, 30 generations, you would expect definitely also a genetic decline. So thank you very much. If Grant is still around, he has this ram's head or skull actually in his office. He died. He was killed by a cougar a couple years ago at Sheep River. Thank you very much.
Thank you, Peter. Very interesting. Personally, I appreciate the energetics component. There's a piece that's still missing, of course, the density dependence and the interaction with the female component of the population. But at any rate, at least you're bringing in energetics for a change.
Yeah, well, and behavior.
Yes, I agree. So any questions for Peter and company? The Q&A box is down there at the bottom of your screen. Yes, we're just about exactly on time, but I think that because of some adjustments in the schedule, we probably don't have to worry about discussion going on a bit longer. If anyone wants to bring up any broader questions as they relate to the entire session on management that we've had this afternoon. It's awfully late in the afternoon, Peter. At any rate, thank you everybody for participating. And what do I do now? Do I turn it over to Kevin? Are you going to wrap up the afternoon here, Kevin? Or
we just got in a couple questions, actually, Mark.
Oh, okay, good. Let's look at those. Okay, Bill Jack says, do you think that habitat interventions enhancement could cloud or hide results of analysis of horn growth change that you saw?
No, I think it has more directly to do with the sex ratios, and the younger males start to be taking a more prominent role in reproducing because they are higher in rank. I think that is the main, I mean, this is the main idea for this model. It doesn't mean that there isn't other things going on as well. Obviously, if you additionally feed the animals, they will grow bigger horns.
So the next question from Kizia Manlov. Peter, I wonder if there might be some utility in thinking about this same issue in deserts. They seem to put off rut participation until later, which might play out in their horns. Curious if you've considered looking into them as a contrast.
Honestly, I did not. I actually have never seen the desert bighorns, but it's a good idea. I mean, it's something that could be looked at. What one would need is to look at their horn increments, at their age development of the horns, and some things like this.
Okay. And then Alice Paquette has a comment or a question here. Given the focus on horn size this afternoon, why are smaller horn sizes perceived as negative? Aside from the trophy implications, the ewes will still select rams that can avoid predators and find good forage. I'm not sure I understand the long-term implications on population beside aesthetics. Very interesting question.
This is actually a good question. I don't think that those rams, if they have shorter horns, that they are less good per se. I think there again the problem lies more into having less older animals. If you think that a 6-year-old is a top ram, it's unthinkable at Sheep River, for example, which is a unhunted population, which is not really unhunted because we still have 30 to 40% of the losses we know of are actually human, be it poaching, car hits, or whatever. So I think the rutting behavior is influenced by having older rams removed because they're really in their prime. When we went to measure this ram that I showed the picture with Catherine, when we went to Cochrane to measure him, there was another ram just coming in. We didn't measure this one. It wasn't one that was originating from our area. It was a legal ram. This ram at Sheep River, he wouldn't be legal for at least another 4 years. And this ram was legal to shoot. So we shoot a lot of rams that would be actually prime rams for the ewes. So I think that's more the problem, not the size of the horns per se.
Good. Well, again, thank you very much, Peter. This has been a very interesting session spanning quite a range of topics, but as is almost always the case in studies of bighorn, there's an obsession with trophy hunting. And rather than managing these ungulates as we manage other ungulates like deer and elk for sustainable yield, we focus on harvesting big rams for trophy hunting. And I think that it's a mistake in many ways. I mean, I think that it gives sheep management somewhat of a negative bent in context of current societal thinking about trophy hunting, and I don't think it's necessary or appropriate. But again, that's my bias. But we have some very interesting talks following up yet tomorrow. So in fact, Marco is chairing the next session tomorrow morning on population ecology. So thank you everyone for attending. And I'm going to log out unless someone has other comments or questions.
Thanks, everyone. Just wanted to pass along a thank you to all of the presenters today and remind everybody that we'll be starting again tomorrow at 9 a.m. with the population ecology, as was just mentioned. So thanks for attending, and we'll see everybody tomorrow for the last day.
Thanks, Jenna.
Have a good evening.